All right, in this worked example, we'll be looking at some projectile motion. And the question reads, a projectile is thrown at an angle to the ground. At a certain time, the projectile has horizontal velocity 23.0 meters per second and a vertical velocity of negative 10.1 meters per second. What is the speed of the projectile at this time? So they're giving us the horizontal and vertical components. So it's like we could calculate the velocity, which would be the vector here, and the angle. We have enough information to do that, but it's only asking us for the magnitude of that vector, right? So the speed is just the how much, it's how fast is it moving. And so really this is just a, using Pythagoras' theorem, right? Like this 10.1 vector we could put over here. We can kind of see what the trajectory is at that point. If we wanted to, we could calculate sort of the angle there and get the full sort of vector information. But all we have to do is, you know, like the negative sign doesn't matter too much here. So it's the square root of 23 squared plus 10.1 squared. All right, so the a squared plus b squared equals c squared, or in physics, we like to call this r for the resultant. And so that's your path to the solution there. Did anybody already solve that? If so, leave it down in the comments below. (23) squared plus 10.1 squared is that number. When you take the square root of it, you get 25.1. So choice C is correct. Now the next one seems a little bit tougher. So this one says, a car of mass 1,400 kilograms is traveling on a straight horizontal road at a constant speed of 25 meters per second. The output power from the car's engine is 30 kilowatts. The car then travels up a slope at 2 degrees to the horizontal, maintaining the same constant speed. What is the output power of the car's engine when traveling up the slope? I feel like I can solve this just by being sort of clever with the test taking. Without really knowing much about physics, it's possible to just sort of size this question up and go, oh, if I was writing a test, this is what I would do. And, you know, so it's more on my knowledge as an educator than as a physics teacher. And so I bet you, here's sort of the relevant physics. Once you start going up the slope, you have to spend more energy to sort of overcome the weight of the car. So initially it's moving at constant speed. And if the car's engine has power, then basically all it's doing is it's counteracting the resistive forces acting against it, right? So there's drag force, there's frictional force, and the engine is just equaling that. So the rights equal the lefts. As soon as we start to go up this slope, we have to overcome yet another force, namely the component of the car's weight that's acting down the slope. So that's calculable. We know the mass of the car, we can calculate its weight. We can calculate the component of weight that's going down the slope. And then, you know, figure out how much power is required to, you know, extra power would be required to do that. And I almost guarantee you, if we were to do that calculation, the answer we would get would be 12 kilowatts. If we were to say, what's the extra power we need to go up the slope here? Because it tells us it's 30 kilowatts is just already, like that's the output power of the car's engine. It's saying, what is the output power of the car's engine when traveling up the slope? Well, we still need all 30 kilowatts that we started here, right? Because there's the same resistive forces, but we need extra power to sort of overcome the component of the car's weight acting up the slope. And again, I almost guarantee you it's 12 kilowatts. And the correct answer then is going to be what? C, 42, because some students will forget to add back in the 30 and they will choose A incorrectly because they calculated that as the extra power needed. So that's just sort of recognizing like, oh, A is the answer that's designed to capture those students that sort of calculate everything correctly, but forget to add back in the 30 kilowatts initially. 42 must be the correct answer. I'm pretty sure, like you should do the math and sort of prove it to yourself. Plus it's good review of the physics, but here's one where you could read the answers and go, you know what, I bet you it's C, just because, you know, 30 plus 12 is 42, right? And they're going to have an answer there that's perhaps designed to capture those students that make that mistake. So for the review here, let's remind ourselves that there's a vector going this way as the car goes up, and that's the weight, and it's equal to mg, and we're given the mass, 1,400 kilograms. And we'll assume this is on Earth, where the acceleration due to gravity is 9.81, or strength of Earth's gravity field is 9.81 newtons per kilogram. So we've got 1,400 times 9.81. And I'll do this mentally, and if you all need a calculator, that's fine. Let's see, 13734. Yeah, I think that's right. Okay. And so we have a component of the weight that's going this way, sort of into the ramp, and then the component that acts down the ramp. I like to kind of draw it down here. So I have this triangle to work with. There's my right angle. This angle here is 2 degrees. And I've already calculated the hypotenuse. So it's really the side opposite that. And again, it's acting sort of this way, right? But it'd be the sine of 2 times this. So the component of weight acting in the x direction is sine 2 degrees times 13,734 newtons. That's all the weight. This is the component of weight that acts down the ramp. And so I'm getting, I'll draw it right here, 479 newtons. So 479 of the, well, I shouldn't say it like that, because the way to add that would be with Pythagoras' theorem, like we did the previous one. There are 479 newtons acting down the slope. And in order to maintain this constant speed, the car is going to have to, provide more power. You may recall that power is work over time, and work is force times displacement. And displacement over time is velocity. So sort of when you're considering a force and power and a velocity, this kind of makes sense here to go to this form of the power equation. It's good review too. Remember, like, displacement over time is velocity, work is force times displacement, so on. Note all the answers are in kilowatts. And so we already had 30 kilowatts in this situation, remember that. And now to move at 25 meters per second with this much extra force, right? We need to provide 479 newtons of extra force to sort of overcome the component of weight that's acting down the slope. We're going to make these substitutions, 479 newtons times 25 meters per second. That should be close to 12,000. My hypothesis is correct. And it is, it's 11,975. Now, don't be so satisfied with that answer that you'll be one of the candidates that chooses A incorrectly. Because like, yeah, 12 kilowatts, there it is. There's the output power of the car's engine. It's not. Exactly what I said to sort of begin. That's the extra power needed. We still need these 30 kilowatts, right? Because we're spending that much power to just move along on level ground. So we add back in the 30 kilowatts to these 12 kilowatts, right? That's 12,000 thereabouts. And the correct answer is C. These have been 2 worked examples with Dr. Schleif for the midterm review, and we'll see you next time.